So linear systems give a much predictable output or response. So for today, our first lecture or this meeting, we will solve a circuit with no excitation, no input. So as we know, circuit elements are passive elements are mainly three types: resistor, inductor, and capacitor. RLC. R is a device which is not frequency dependent. L and C are frequency dependent. Okay, so we will use this to our advantage, and they will generate linear ordinary differential equation with constant coefficients. Or also these are lumped elements. They are also distributed elements. Now let's examine without input, uh, analyze a circuit. Consider RL circuit, only resistor and inductor. So how will we analyze this circuit? We know that this is already an LTI system. It will generate linear differential equation with constant coefficient. So and as this system abides by superposition principle, we can apply KVL or KCL. Now what should we apply? So inductor is a frequency dependent element, and it can store energy or release energy. Okay, so if it does that, then we can say inductor is considered to uh, store initial current. So if we say it stores initial current, okay, I O equals to I plus initial current, then what will be the response without if inductor only has initial current and there is no excitation, no input in the system, what will the response of the system? So we will use the KCL law or KVL law. Each can be used. Okay, so by KCL states that um, sum of current at node, sum of current minus sum of current uh, to the node and out of the node is 0. And KVL in a loop, in a circuit loop, voltage rise minus voltage drop is 0. So we will use this to analyze this system with initial current. Circuit analysis will be done by these two methods, time domain and frequency domain analysis, by considering the circuit as system, as an system, and which is an LTI system. So now we will use the KVL rule to use to get the circuit analysis, to analyze the circuit or get the circuit response by KVL. By KVL is this. Okay, so by KVL we know that in a loop, this forms a loop. In a loop, voltage rise and voltage drop is equal to 0. There's no voltage rise, only voltage drop. So as this is an LTI system, this RL circuit is an LTI systems with initial current, we will analyze this circuit in two ways, two methods. One is time domain method and the other is frequency domain method. So let us first analyze this circuit in time domain. So let's say time domain analysis. Time domain analysis. Okay. So by time domain analysis, let us use KVL. KVL, Kirchhoff's voltage law, in a loop. This forms a loop RL circuit with no input or excitation. So what will be the equation? Okay, for this current, um, R plus L di by dt it, no excitation, equals 0. This is KVL. V1 by plus V2, VR or VL equals 0. Now this is equation. Let us assume d by dt equals d, which is called linear differential operator. We will use this throughout our my lectures, uh, as a calculating element. Okay, linear differential equation in solving the homogeneous non-homogeneous linear differential equation with constant coefficients. You can see this, that it forms linear differential equation with constant coefficients. That's why this is an LTI system, or because this RL circuit is an LTI system, it forms linear differential equation with constant coefficient. Now for uh, circuit and this equation, there are two parts. Okay, complementary part and the particle integral part. So this will obviously give linear ordinary differential equation, will give constant coefficient, will give complementary particle integral. So in circuit analysis, the complementary part is called transient response and particle integral is called steady state response. Okay, so we will first analyze the solve the for the complementary equation. For complementary equation, we say that for complementary or transient response, complementary solution or transient response, R plus LD equals to 0. This is also called characteristic equation. Characteristic equation. Okay, so we are going to solve the characteristic equation, which will give us the transient response. So let us first make some space. Okay, now R plus DL equals to 0, or D equals to minus R by L, which can be called lambda, which is the character eigenvalue. Okay, so we found our uh, complementary solution. Now the real solution, for we get our value for complementary transient response. Thus transient response is um, it equals to e to the power minus t R by L. What is this? This is, say, A. This is the transient response. So we have now, what we have to do is find A, and for particle integral or steady state response, there there is none, because there is no input. Steady state response of particle integral is only present in a system when there's an input or excitation. Okay, so the particle integral is 0. So steady state response is absent. in source free, obviously there's no source, RL circuit. Okay, so all we have found our solution for source free RL LTI system or RL circuit in general. So we just have to find a the function. There's no minus. Okay, now we know that IO 0 t equals 0 is the initial current, which is a to the power 0 1, thus which gives a equals to IO. Thus response is IT equals to IO e to the power minus T R by L. This is the response or analysis of the source free RL circuit, which is also an LTI system, and we got the time domain analysis. Now we will do the frequency domain analysis. Now the frequency domain. So how are we gonna do analysis in frequency domain? So there, which is where the LTI system, its properties come in handy. Okay, because the electrical system is modeled as LTI system, it will obviously give some transformation technique advantages. Okay, so because the system is LTI, we can apply Fourier Laplace transforms. Okay, Fourier Laplace transform LT and FT in frequency domain to find the circuit response, or analyze the circuit in frequency domain. So in frequency domain, the elements is transformed. So what will be the element in frequency domain? Okay, now in frequency domain analysis, okay, FDA, frequency domain analysis. Now in frequency domain, as R is independent of frequency, it will be the same, but L will have an S in frequency domain with it. We are doing the Laplace transform, okay, to get the full response. Laplace transform gives the complete response, or we can find the complete analysis of the, we can analyze the circuit completely. But on the other hand, Fourier transform is only good for steady state response, or response when excitation or input is available. Okay, that's when we do the Fourier transform. Okay, as the circuit has initial current, the inductor in specific terms, so it will have in Laplace domain an extra current or voltage. Okay, so now in, okay, in Laplace transform, Laplace and this is inverse and this. Now in frequency domain, we are doing frequency domain analysis. Okay, so this is R, and this will give, as this is LS in, as a inductor is frequency dependent, after an LTI system, after Laplace transform, it will have, it will also, the inductor will also be transformed, and it will have an extra source. If we say this is a voltage source, it will have Li. This is the Laplace transform with initial current in the inductor. Okay, this is and if we replace the initial current with voltage source, it will be this. If we replace the initial current with current source, it will be this. With initial current, it will be like this. this is SL and this is I O by S in Laplace transform. Now what are we gonna do in Laplace transform? Okay, so Laplace transform, what does Laplace transform does best is it transforms this circuit into an LTI system which will generate an linear algebraic equation. Okay, so for Laplace transform we are gonna see that, so initial current it will be minus L I 0 means IO equals to 0. This is the basic uh, system, so which will give R plus SL. Now if we transfer this L IO, okay, this is the basic by KVL. Okay, this is voltage and this is voltage, sorry, current. My initial current with L is voltage. This is KVL by KVL in FDA by KVL. Obviously you can also use KCL, it will be your homework. Do it, analyze the RL circuit as LTI system using KCL. Okay, so let us solve this. I S equals to L IO by R plus SL. Okay, L, let me show you how. R by L into L. Okay, which will, this gives this. Now what's happening is this is gone. Okay, and we know by uh, Laplace transform formula that if we now um, uh, inverse Laplace transform this, which will give by inverse Laplace, by inverse ILT, inverse Laplace transform, IS becomes IT again, IO is IO, it's a constant DC value, and this becomes e to the power minus T R by L, which is the same as the answer in time domain analysis. This is answer. Okay, so we found our time domain and frequency domain analysis in terms of LTI system. So this is our circuit, which is LTI system which generates linear linear differential equation with constant coefficient and in time domain. In time domain, the circuit response or the complete circuit analysis by from the complete circuit analysis we get the current IT equals to initial current e to the power minus T R by L. This is in time domain. In frequency domain we get the same answer. Okay, IO e to the power minus T R by L. So this is the answer. If electrical circuit is considered in terms of signals and system, it is an linear time invariant systems, and linear time in linear system abides by superposition principle, which allows us to apply KVL KCL over them. By applying KVL KCL we get in time domain linear differential equation with constant coefficient, which gives us this answer. And as the system is linear, we can transform the system to our liking by Fourier Laplace transform. By Laplace transform gives us the complete circuit response, or we can analyze the circuit completely for any time. Okay, now by Laplace transform we get this transformed circuit, um, uh, this transform or this. Okay, the we use the voltage analogy, not current source analogy. We use the voltage source analogy. Okay, voltage source analogy gives uh, minus plus LIO, and this is IO. You can replace it IO LIO. Okay, so by using KVL also, because Laplace transform fully converts the differential equation into algebraic one. So by that we use KVL obviously, because it's linear in frequency domain also, and got our answer. The same answer is this. Now that's it for today. I hope you understood. If you have any question, you can write on the comment section. If you have any problem with my solving technique, you can say that in the comment section, and I will try to come up with different solution methods and circuits. I am trying to solve almost all kinds of electric and electronic circuits, and I will in future come up with topics and problems in EMF. Okay, so stay tuned and please subscribe to my channel. I am greatly hoping that you will like my content. That's it.